Okay, so now we come to Newton's third law. Newton's third law says that if objects 1 and 2 interact, then the force 1, 2 exerted on object 1 by object 1 on object 2 is equal but opposite. Draw a picture of what that means. Or in fact, you can do this right now. If you push down on the desk with your hand, you're pushing down with a certain force. And then your desk is pushing back up with that same force. So for example, if I push down with a certain force, my hand or with an object or whatever, I'll call this F12. Then there's an equal but opposite force that's pushed up by the table, and I'll call that F21. So anytime you have a force that's pushing in one direction, you're going to have an equal and opposite force that's pushing in an opposite direction. This is an equal and opposite force. This is true for contact forces, obviously. Anytime we have a contact force, we experience this, this law, but it's also true for field forces. And that might be less obvious, but if you remember when we drew this picture of the two masses, remember they had equal and opposite forces. From Newton's universal law of gravitation, those objects had equal but opposite forces. And so the result of this law is that no isolated force can exist. If I ever have one force, then I have to have a second force. And that's kind of interesting. All right, so what about the force due to gravity extended on you by the Earth? Is this an isolated force? So, you know, I'm standing here on top of the Earth. And I feel a force that's pushing down on me about, say, 700 newtons or so. Is that an isolated force? Well, the answer is no, because as we walk around on the planet, we're actually pulling back up on the planet with a force that is equal and opposite. Remember, Newton's universal law of gravitation, it doesn't matter how big one of the objects is, they're both still going to be pulling on the object with the same magnitude, but opposite direction force. So the Earth is pulling down on me with 700 newtons, and I likewise am pulling back up on the Earth with 700 newtons. All right, so as I said, contact forces also obey Newton's third law, and the result of this is something we call the normal force. The normal force is, look on the next page here. Normal force results when you have an object that's sitting on a surface. This is the simplest scenario. Have an object sitting on a flat surface. It is flat, even though it doesn't look flat. I have a force weight that's pushing down, and then I have another force that's pushing up. And that's called our normal force. Now, normal means perpendicular. And that's where this comes from. It is the same as perpendicular. That's the mathematical definition. And so this force, this normal force, is always perpendicular to the surface of where the force is being applied, always perpendicular to the surface. Now, since the acceleration in this case is 0, since it's stationary, then I can say that the sum of the forces equals ma. And so the acceleration equals 0, so this equals 0. And the sum of the forces are the normal force, which is up, minus the weight, equal to 0. So often, at least when we have a horizontal surface with an object just sitting on that surface, the normal force is equal to the weight, and this is why. But it's not always the case. We'll see that on inclined planes that this is not true, that the normal force is not equal to the weight, but often it is. Anytime you have an object that's sitting on a flat surface. Now, caveat to that is, let's say I have an object sitting on a flat surface. Right, I have a weight, Fw. Well, let's say that I also have another force, like say I'm pushing down on a block with just some force. In that case, the normal force will equal the weight plus this other force because I'm pushing down on it. And so as a result, the table is pushing back up again. Let's see, I've already said this, but normal means perpendicular, so normal forces are always perpendicular to the surface. All right, let's look at this. So this is a an object, an inclined plane, and you'll see an inclined plane on the next quiz. But I have an object that's resting on an inclined plane, and the normal force is equal to the y component of the gravitational force. So I can, I have these forces. This block is just sitting on the surface. There is a weight pointed up or pointed down like that, and then the normal force. Notice it is not pointed up, but it's pointed perpendicular to the surface. And I want to find out what is the normal force. So let's say, for example, this angle is 30 degrees. That means that this angle is 60 degrees. I can find the components of the weight. I have a y component. This is going to be Fw sine of 60. And then I also have an x component, Fw cosine of 60. And so if I look at the forces in the y direction, the sum of the forces in the y direction equals Fn minus Fw sine of 60. So in this case, this object sitting, oh, and this is equal to the mass times the acceleration, but the acceleration is 0, so that's equal to 0. And so the normal force is equal to Fw sine of 60. That's for an object that's resting on an inclined plane. Now let's look at this Mcat example. I have the mass of the box in this figure is 10 kilograms. I want to know what force directed up the inclined plane will have to be exerted so that it's stationary. So I want to know what is this force F so that the block is stationary. All right. Well, if I look at my forces in my x direction, then well, let me redraw this. So I'm going to redraw this with my vectors now resolved. So here I have Fn, I have Fw sine 60, I have F, and Fw cosine 60. Now I can apply Newton's second law, and I've already done that for the y, but I'm going to do it for the x. Sum of the forces in the x direction equals MAX. The sum of the forces in the x direction are Fw cosine 60 minus F equals MAX. AX happens to be 0 in this case because it's stationary, so that's equal to 0. So I can solve for F, and F has to equal Fw cosine 60 in order for this to remain stationary. So let's see, it's 10 kilograms, so we'll call that 100 newtons times cosine times the cosine of 60, which is equal to 50 newtons. Notice here, this 100 newtons, let me just point that out. I just said M times G. I said 10 kilograms, and then I used 10 meters per second squared, just rounding up that 9.8. All right, so that's 50 newtons. Now, I've had a method here. My first method is to label the forces. My second step is to draw a vector diagram. Now here I've sort of combined those steps. I've labeled the forces and I've drawn my vector diagram in this step right here. In the third step, I resolve the vectors. I resolve, and that's what I've done here. Step 3, resolving their vectors into their x and y components. And then finally, in the fourth step, I apply Newton's second law. I say the sum of the forces equals MA. And those 4 steps will be the same throughout. By the way, this is that 4th step right here. These 4 steps will be the same throughout all of these Newton's laws problems. You label the vectors, you draw a vector diagram. That just means I put them onto a coordinate system and I figure out what all the angles are. Then I resolve the vectors and their x and y components, and then I apply Newton's second law. All right, we'll come back to this quick test. We'll come back to this. I'll pause here.